Hi, and welcome to my presentation on vibrational radar backscatter communications at IEEE's ASILOMAR conference on signals, systems, and computers. My name is Jessica Centers, and I'm a PhD candidate in Dr. Jeffrey Kralich's lab within the Electrical and Computer Engineering Department at Duke University. To begin, I would like to break down the title and provide motivation for our work. Radar backscatter communication, or the method by which an RF signal is transmitted and reflected in such a manner that contains a message signal, is most commonly exemplified as RFID. This technology is used for tagging and Internet of Things applications. Radar backscatter communication is typically limited to frequencies below a few gigahertz, or within the UHF frequency range, due to the need for efficient transponder re-radiation from the original RF illumination. Though millimeter wave technology has recently become available and inexpensive thanks largely to the push towards autonomous vehicles, radar backscatter communications at millimeter wave frequencies has only been able to achieve adequate signal returns through solutions such as using expensive retrodirective antenna arrays. In this work, we instead propose using millimeter wave radars as vibrometers to detect vibrational transponder communication signals, thus eliminating the need for complex antennas on the transponder. One application of particular interest for this technology is vehicle-to-anything communications, acronymed V2X. V2X's primary goals are safety, energy savings, and traffic efficiency. This is broadly achieved by improving a driver's awareness of potential dangers, providing traffic information, suggesting alternative routes, and informing the driver of other useful things like available parking spaces, local weather, or the presence of emergency vehicles. Currently, there are two categories of standards for V2X: dedicated short-range communication, DSRC, and cellular V2X, which also includes LTE V2X. Both of these standards suffer from increased signal interference and transmission latencies due to networking and increased traffic situations, as they have a select amount of channels designated for this application, and they therefore must either take turns and incur delays or suffer in performance from interference when a large amount of users in a particular area are trying to use them. So how exactly will VRBC, or vibrational radar backscatter communications, solve this issue? Well, by using a millimeter wave radar, which is already used in cars for detecting, classifying, and or tracking other objects, vibrating targets can be detected and the message signal can be modeled as the vibrational displacement of these targets or transponders that appear in the phase of the return. In this system, we are no longer limited to the 7 channels traditionally accustomed to V2X systems. Here, the effective number of VRBC channels can scale with the range and bearing resolution of the radar being used, without introducing mutual interference among transponders. The radar we're using in our experimental research here is this Texas Instruments IWR-1443 automotive radar. It operates at 77 gigahertz and has a 4 gigahertz bandwidth, which provides as small as 3.75 centimeters range resolution. The 3 dB bearing resolution for this module is plus or minus 28 and plus or minus 14 degrees in the horizontal and vertical dimensions, respectively. Another key characteristic of this radar to keep in mind is the maximum pulse repetition frequency. For this radar, it is 25 kilohertz. Since PRF is directly proportional to the sort of data rates we can expect to achieve in this system, we desire to operate as closely as possible to this maximum PRF. The transponder we're using for this research is the commercially available iHome loudspeaker, also shown on this slide. Specifically, we're only using one of these loudspeakers, though the picture shows 2. It has resonance at around 210 hertz, which is important to note, as resonant frequencies provide larger vibrational displacements, which equate to larger phase changes, which increase the phase signal-to-noise ratio. In summary, vibrational backscatter communications then essentially works by inputting whatever message signal we choose to transmit to the loudspeaker, which closely relates to the physical vibrational displacement of the loudspeaker diaphragm, and observing the radar return from the transponder loudspeaker. That vibrational displacement then appears as a phase change in the return or backscatter. An application, I should mention that the transponder is not necessarily a loudspeaker. In fact, it probably won't be. It could easily be something like a vibrating license plate or even a vibrating bumper. To begin, we modeled the return. Naturally, This model includes the backscatter specific to the transponder or target, whichever word you'd like to use there. Also includes the clutter, which includes stationary and Doppler compensated constant velocity objects, and complex additive white Gaussian noise. In this equation here, you can see all three of these components. The transmitted waveform is labeled as S sub tx, and the appropriate delays for each of these components are accounted for and shown in this equation. Some quick notation in this work includes that R corresponds to range with its subscript providing indexing information, C is the speed of light, and K is the number of clutter points considered. Also, you can note that a tilde in these equations just indicates that the variable is complex. In working with this model, we assume that the vibrational displacement of a transponder is insignificant on the baseband chirp waveform. So in other words, this simply means that because the range resolution is larger than the maximum displacement expected from these transponders we're using, the target return does not jump across range bins in fast time. Additionally, these alpha terms that we're using here are complex Gaussian terms whose phases are uniformly random, and the mean of the magnitude squared corresponds to the power of the return. These are justified by the swirling model because a given scatter is assumed to contain multiple reflecting surfaces. We also assume that ranges are not time dependent. In other words, without loss of generality, we assume that relative velocity has been accounted for. After dechirping, beamforming, and range processing, the channel model becomes y of t as shown here. Here, lambda is the wavelength associated with the 77 gigahertz operating frequency, and k prime is simply an indication that not all of the k points from the previous equation make it through once we do the beamforming and the range processing, and we've selected the specific location bin of our transponder. Now, to formally show the channel model output y of t and how it's achieved in processing, let me describe the full processing chain. First, we conduct target detection. Traditional CFAR detection is done in microdoppler in range on the cluttered filtered data. This means that to be detected, the vibrational displacement signal d of t, which again appears in the phase, must provide return that has large enough non-zero hertz Doppler content such that it is detectable against the background noise. Keep in mind that arbitrary d of t signals tend to have some 0 hertz Doppler component, again, since that d of t does appear in the phase of the backscatter. Once detected, a target or transponder is isolated, or in communication terms, its specific channel is chosen, which again is just done via spatially isolating the return in both range and angle, so therefore beamforming and range processing. Then a quick synchronization is conducted using a preamble sequence whose microdoppler has good autocorrelation properties in order to detect the start of our communication signal. Once we have found the start of the transmission, demodulation of the message signal is done through optimal M-array transmission symbol classification. We use base test for a set of M symbols, all of which are the exact same length and time denoted by T sim, and also the same length and number of samples per symbol, which is denoted by L sim. Here I show the observed data vector given that symbol I was transmitted, so that's the R given H sub I, hypothesis I. On the bottom, the likelihood statistic L sub I for the given return R is then calculated as shown for each symbol type, and the symbol that the classifier declares for each symbol interval is then whose likelihood statistic is greatest. This is just your traditional, again, M-array optimal base test. A few things to consider in our message signal design is what symbols we use. In our model, this corresponds to choosing what the various D sub I of T signals are going to be for I equals 1 to M, where we've got M symbols being used. As mentioned, we first desire to minimize the 0 hertz Doppler such that the transponder or target detection is optimized. Secondly, it is optimal to choose DI of Ts that provide complex data vectors that are orthogonal, as this minimizes error. This is actually quite difficult in practice, and I'll show you that on the next slide a bit. Thirdly, we want to consider the capabilities of the vibrational transponder, which for us is this iHome loudspeaker. For example, speakers cannot vibrate as a perfect square wave. In this figure on the slide, I show the frequency response of our speaker in terms of maximum displacement versus frequency to demonstrate that we cannot even expect to achieve symbols for which gamma in that top equation on this slide is above 30 micrometers at frequencies higher than 400 hertz for the specific transponder. And so that's important to note. Experimentally, we begin with that iHome loudspeaker whose frequency response I just showed you sitting about 1 meter away. Also pictured is our laser Doppler vibrometer, which we used for verification purposes. In the result that will follow in the next few slides, we choose to use 2 different sets of 4 symbols, so m equals 4. These are our DIFTs for I equals 1 to 4. First, we choose sinusoids as they're easy to produce. Unfortunately, though, this FSK symbol set does not even provide theoretically orthogonal data vectors. So for this reason, we also considered an ASK symbol set of sorts, which uses triangle waveforms. Though these are theoretically orthogonal, it is important to note that they are not orthogonal in reality unless the maximum displacement and amplitude is calibrated 100% accurately, and the loudspeaker is able to perfectly produce a triangle wave displacement, which it is not. So these are both difficult to achieve in reality, but for purposes of experiments here, we tried. Using equal probable symbols and the processing chain previously described, a long set of symbols were played on the transponder and received via VRBC to the radar. To see how good of a data rate we could achieve, we varied the symbol length, which required adjusting the radar parameters. On the bottom axis, you can see that to achieve higher data rates, we began by increasing the PRF from 2.5 to 5 to 10 kilohertz, which is essentially increasing the sampling frequency of our signal. We then became restricted by the capabilities of the radar and had to decrease the number of samples per symbol, which is LSIM again, in order to keep increasing the data rate. This is shown by transitioning from one color zone to the next. It was found that with 25 samples per symbol, we were able to achieve perfect performance for no symbol or no symbol classification errors, essentially. Once we dropped to 5 samples per symbol, this was no longer the case. As indicated in the blue speech bubble, the other way we could try to achieve higher rates is by using more symbols. So that's exactly what we did next. Note that on the next slide where I show these results, we're using the 25 LSIM moving forward, since for m equals 4, we were able to achieve perfect performance with that. Here we have performance versus the increase in M that I was talking about for the quickest 2 baud rates used in the previous experiment. As you can see on the left, when the PRF was 10 kilohertz, we achieved up to 1.2 kilobits per second experimentally perfect data rates for both symbol sets. Then on the right, even when we used the slower PRF of 5 kilohertz, which equated to symbol lengths of 5 milliseconds, we achieved about 1 kilobits per second experimentally perfect data rates. In conclusion, what I have shown is that VRBC could provide a communication solution in applications such as V2X, where networking delays and or signal interference is a concern due to the limited amount of channels, since it is allowing a channel to be available at each location bin visible to the radar, thanks to its spatial and bearing resolution. Additionally, I've shown that symbol design is important and tricky. Not only that, it is transponder dependent, making the choice in transponder very important. Thirdly, we have already demonstrated that a minimal achievable performance is at 1 kilobits per second. Moving forward, we aim to adjust our model to account for vibrational noise that is present due to the inherent vibrations of the surface the transponder or radar are mounted on, such as a vehicle in the V2X application. This could be done potentially by assuming that an adjacent location cell contains the noise, but not the transponder signal, and then adjusting the transponder signal using that adjacent location cell's signal. Moving forward, we would also like to experiment with other transponders, as it is obvious that loudspeakers are specifically designed to provide good acoustics and not necessarily good vibrational displacement. With that, I'd like to thank you for listening to my presentation. Here are a few of my key references. On this slide, you can also find mine and my advisor's email. Thank you.